So let's look at the zoo of examples. First, we have, and part of it's just the names. We're going to give, so we're going to say these are the real numbers, and we're going to say the n up here is the number of rows, and we're going to put a c here for column vectors. So this is the name of a set of vectors, which is like x1 up to xn, such that x sub I is a member of the real numbers. Now you'll notice this is also a solution set of one of our systems where all the variables are free, right? So for example, the one we've dealt with most simply is R2C, which is just, if we just have two, we could call it X and Y, so we don't have to, we leave the indices here to sort of make the general statement R to the N, but then if we have just two or three, we could use XY or XYZ. So this is where X and Y are real numbers. Okay, and this would be like, one of our, if we have this as a linear system in two variables, sort of like 0x plus 0y equals 0, then this would be the solution set. So the solution set of certain linear systems, you can see right away, that's the connection. Here's sort of the spoiler alert. The solution set of a homogeneous linear system is a vector space. So it's going to come in that the vector spaces are descriptions of solution sets by and large. Okay, so there's our first example. And our second example, this seems like, why would this really be different? But we can put an R here and an N and say, well, these are so these are column vectors. And these are, of course, row vectors. And it's a little bit, it seems, they're not that much different because, what's the difference between writing them horizontally and vertically? Well, they interact in certain ways, when you put but then still, as vector spaces, they're just two different kinds of objects. And it's useful sometimes to treat them differently. So it turns out that it isn't just sort of like, oh, I drew the numbers horizontally or vertically. There's something going on that represents that, but we're not going to get it. And also, we're going to work with column vectors because row vectors look a lot like coordinate tuples. Like if I write here, X, Y, let's just do 2 dimensions, X, Y. You're used to that. You're used to thinking of that as just the coordinates of a point in a plane. Well, that's not very good coordinate axes. Let's see if we can do a little bit better. So here's the x-axis, the y-axis, and you have some point, and then you might have like 1, 2, and then this is the coordinate pair that goes with this point. So we're not, but then coordinate pairs, you don't usually like add or subtract them. So row vectors are like coordinate pairs with extra properties that you can combine, add and subtract them. We usually don't add these coordinate pairs because they're just locations. They're just like map coordinates. So there's a difference between, but then because this is so similar to what was the difference in a comma, we're going to use column vectors. And also matrix multiplication is defined in terms of column vectors, matrix times a vector, not, and you can define it in terms of row vectors, but we typically have not done that. Okay, so that's our second example. And our third example, which is a little bit more involved because we haven't dealt with it so far, are arrows in Euclidean space. Well, what does that mean? Well, it's geometry, and Euclidean just means that, well, think of a plane. I have a plane, and I have 2 points in the plane. It's 2 points determine the line, right? 2 points. This is the geometry that you learned if you were in the American system in ninth grade. 2 points determine a line, and then so you can draw a line through the 2 points, and you can make triangles, right? Like this, and this if you have this length here and you have this length here, and so they have there's things that have lengths, then you have the distance between these 2 points is related by h squared equals a squared plus b squared. That's Pythagoras' theorem. So, and that's what you mean by if Euclidean space is sort of flat. There's other spaces that are curved, like the surface of a sphere, in which if you wanted to say do the geometry of navigation of planes and boats on the sphere, you can't use Euclidean geometry because you're stuck on a spherical surface where this if you draw like a straight line, is not quite going to be satisfy this. And then also there's something with angles. Like I might have like alpha, beta, and gamma. And if it's Euclidean, alpha plus beta plus gamma are going to equal 180 degrees. Now, there's some other geometries where on a curved surface, like if it's large enough, and you sort of draw, like took a laser or something, or took and sort of looked across, or maybe not a laser, because that would be a straight line. But if you sort of went on the surface, sort of what would count as a straight line, and then you sort of made a triangle, well, the angles that you'd measure wouldn't necessarily add up to 180 degrees, and you wouldn't satisfy Pythagoras' theorem. So we're not going to deal with spaces like that. You might be happy to know. So we're only going to deal with spaces that are flat. And that's the natural concept. So we have the Euclidean, Euclid, I don't know how to spell Euclidean. That's not even Euclidean. There you are. Something like that. Euclidean means flat. And you notice, remember that a linear system, if we look at the solution set from chapter 1, if you remember back to that chapter, there was an equation, a linear equation is the equation of a line, but that's the equation of a line in Euclidean space. So the solution sets of linear systems are all flat spaces. So now we're going to call these like E1 is a line, okay? E2 is a plane. Try to draw that in perspective. E3 is like a 3 space. We normally do like X, Y, Z. E4 is hard to visualize because our space is these are called dimensions. This is like 2, 3-dimensional, and this is hard to visualize. You can sort of imagine like time being the 4th dimension. This is what physicists do, when they want to talk about special relativity or science fiction or whatever. And you can sort of think of, well, you have like a sphere, which is the Earth, and you can sort of think of it as at different times. This is my rendition of a sphere. Looks more like an eye, but okay. But you can imagine this is the Earth. Okay, so you can sort of say, well, it turns out that inside the 2 space, we could have, this would have variables X and Y for coordinates, and we could draw a line here, and that would be a linear system in 1 variable. And if we draw a plane in here, what would characterize that plane would be something like X plus Y plus Z equals 1. A linear equation in 3 variables is going to sort of chop out one of the variables, and you're left with a plane. And this structure, if you ask for all the X, Y, Z triples of numbers that satisfy this equation, they'd fill out a plane in this space. And the same thing would happen with E4. If I took a linear equation, x plus y plus z plus t equals 1, this would fill out a flat 3 space, sort of one of these inside here. You can sort of think of, well, you'd have all of space at time 1, all of at time 0, all of space at time 1, all of space at time -1, or you could have a plane moving through time. You could have sort of like one plane like this that would just be the same flat space, but it would sort of fill out like in time. It would be like a bar or something like that where you'd see anyway. So that it gets progressively harder to visualize these higher spaces. And you might think, well, because our space is 3-dimensional, this is really sort of academic. But the problem is that in subjects like economics, where you deal with abstract systems, you might have a vector space that's much larger, that's 3 or 4-dimensional. And if you deal with, for example, at the end of the course, we'll have an application in epidemiology with epidemics, and there, your space has to do with how many factors you're taking into consideration. So you might have a linear system that's relevant that could have 10 variables. So you can't visualize stuff like that, but you can deal with those kind of spaces with linear algebra techniques. So what you do is you can use the intuition you get from 2- and 3-dimensional and maybe 1-dimensional space to understand these higher dimensions. But the calculations you actually do are all with, just these variables. Okay, so how do we deal with this? Well, let's deal with E1, because our vector space, what counts as vectors are arrows. Arrows are vectors, but they're going to be mobile vectors. They're not like they're mobile arrows. So, for example, let's say that this has a length of 2 units. This has a length of 2 units. This has a length of 2 units. This has a length. All these cases, all these arrows, all the same vector. If you want an analogy, think of this as a car moving to the right, going 30 miles an hour. Well, it's going to 30 miles an hour here. Even though it's moved to this place, it's still going 30 miles an hour. It's still going 30 miles an hour. So the vector, the direction of magnitude that describes how fast it's going in what direction, hasn't changed. It's the same vector, even though the car is at different places. So we think of that as the same vector. So you can think of this as sort of like if you've taken physics or mechanical engineering, these are sort of like differences of positions. Okay. But we don't have to do it. We can just think of them as slidable arrows that you can move around, okay? And then you also have arrows that are pointing, say, here's one going the other direction. It's 3 units to the left, right? Now, what we can do is we can make a connection between these arrows. First of all, we're going to end up with, I've defined some sets here. But what makes it a set into a vector space? Well, what makes a set into a vector space is not just the set, but how we combine them. So what we need for each vector space is a way to combine vectors to add them and multiply them by a number. Okay? So what's going to make this set into vectors is a way of adding them and multiplying them by numbers. What makes this set the same? What's going to make this set the same? So let's go back and see what are the operations for R. Let's do R C3, in which you have your X, Y, Z, say 1, 1, 1. This is V1 plus V2, which is X2, Y2, Z2, is just what you think it is. It's just X1 plus X2. It's just vector addition to what we did in chapter 3 and even chapter 1. Yeah, this is the column vector thing here. So this number here is, I have 3 rows, 3 components, and the column vector says that I have the column vectors rather than row vectors. Z1 plus Z2. Well, there's my addition. So this operation that I can add vectors is what's going to make this into a vector space, along with the fact that if I take any vector and multiply it by a real number r, it's defined by rx, ry. So this is the set of 3 column numbers that are defined up here with these operations tell you what you mean by a vector space. Okay, so now if we come back and we ask, well, what about this space? If this is going to be a vector space and we have these arrows, we have to be able to add them and multiply them by numbers. Well, so here's our addition. What we're going to do is we're going to take an arrow. This is an E1. This is a one dimension, sort of like a line. Okay, so we have this one. It's 1, 2, 3, 4, 5, and we have 1, 2, 3. So we have V1 and V2. It's just on a line they're pointing in. We also have to deal with the case of, say, adding it to V3, which is going the other direction, right? But what we're going to do is we're going to define V1 plus V2 is going to equal the vector, that is the arrow that you get by the following construction. This is 1, 2, 3, 4, 5. 1, 2, 3, 4. I put the first one down. Then I put the second. These are movable, right? I can slide them around. So I can take this one no matter where I found it and put it over here as 1, 2, 3. And say, well, I put it tip of 1 to tail of 2, right? So this is the tip, and this is the tail, where the feathers would be if this was a physical arrow. And so you put it this way, and you define the sum as the arrow that starts from the tail here and goes to the tip here. This is just the definition that you would have 1, 2, 3, 4, 5, 6, 7, 8. So we have 1, 2, 3, 4, 5, 6, 7. So we'd have V1 plus V2 is this. Now, this sort of looks like, well, if this is like 5 long and 3 long, this is 8 long. It looks like you're just adding them, but something funny happens when you add V1 plus V3, because you do the same rule. 1, 2, 3, 1, 2, 3, 4, 5. Then I put this one up next to it, tip to tail, and it comes back here. And if I start here at the tail and go to the tip, this vector, the squiggly vector there, which is only 2 long, is V1 plus V3. Okay, well that deals with sort of all the cases of addition of vectors that makes arrows in E1 into a vector space. But we also have to know, well, what is 3 times V1? What do we do 3 times V2? Well, this just stretches the length. So if V2 was 3 long, 3 by 3 is going to be 9 long. So I'm going to have, here's V2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here is 3V2. It's 3 times as long. So the vector 3V2 is just the arrow that's 3 times as long as this one. Okay, and then you can also see, what about negative numbers? If I take minus V1, well, that's going to be the vector that flips the direction but doesn't change the length. So it's going to go, instead of 3 to the right, it's going to go 3 to the left. This is minus V2. So we're going to say that we can give a name to this one as, if this is V2, this is minus 1 times V2, and we can call it minus V2. So these two operations together are the analog of these two operations here. And then we can make a connection between the two to see that, well, we can look at all the properties of these, and we can look at all the properties of these. And it turns out that with these definitions and these definitions, they pretty much have the same properties. So, and this is sort of the key thing that physics and mechanical engineering does. The physics is in the arrows and this, like forces and velocities and modeling the real world, but then the calculations you do are done by making a connection between these arrows and these numbers, and then doing calculations with the numbers, because it's hard to do calculations with geometric diagrams. Now, this works for E1, but what about E2? Well, your vectors are still arrows in a two-dimensional plane, but they can go in different directions, right? So, but I still have to be able to add them and multiply them by numbers. So multiplying by numbers isn't hard. You just keep the same direction and make the length longer or shorter, and this minus sign changes the direction. So the only thing that's really new is the addition, but you use the same rule. Like I'm going to take vectors that I can draw more clearly. Here is V3, and I want to add to it, say, V4 here. So what I do is I draw the first, so this, I'm going to construct V3 plus V4. Well, V3 plus 4, I put V3 down anywhere I want, then I put V4 down tip to tail. So I can't change the length. So when I mean this vector here is the same as this vector here with the same length, this vector here is the same as this vector here. If this is the same length and direction, they're slidable things. They don't have locations. So I can slide those around, but I can't change the direction. So if I put this here, I put it tip to tail, tip of 3 to tail of 4. So it's tip to tail. Then the arrow that starts at the tail and goes to the tip, that's V3 plus V4. Okay? And you can see that you get all kinds of stuff going on as V4 can be in different directions and stuff. And you have some geometry here. Okay, now it's going to turn out that I'm going to be able to make a connection here between these vectors and these vectors. And this sum, if this is x, y, 3 and 4, and x, 3 rather, and 4, and this sum is going to capture this geometry, and they're going to behave in the same way. So I may set this up as to model some physical situation, but then I can convert it to these column vectors and do the sum, and I'm going to get whatever's going on in the geometry from algebra. Okay, so that is the value, and the connection is going to be fairly straightforward. We're not going to deal with this connection explicitly, but we need to you want to see how it really works. So if I take a vector here, V, to make this connection, I have to choose some standardized directions like X, which are sort of like your coordinate systems. Here's V. And Y, but I don't want to put it at the origin. I just want to put, here is, so I have some coordinate axes that allow me, I choose an origin, I choose a direction here, I choose a direction here, then here's my vector. Like that. Well, what I do is I have some coordinate points. Like this is 3 and 2, and this is 3, 4, 5, 6, 7, 8, 9, and 4, right? So I'm going to associate this point here. I'm going to associate this with the vector of, this is sort of the coordinate points of this one is 3, 2, and these are the coordinate points of 9, 4. So those are coordinate pairs. This is just the point 3, 2. This is the point 9, 4. So what I'm going to say, the vector is going to be 9 minus 3 and 4 minus 2, which equals 6, 2, right? So this vector can be anywhere. It's the vector that always goes over 6 and up 2. So I can move it in different places. So this vector is the same as this vector, 1, 2, 3, 4, 5, 6. This vector here, these are the same vector. Because if I did this one, then it would be 0, 0. and 6, 2. So 6 minus 0 and 2 minus 0 be the same thing. So this is how you make the connections. You do the geometry of the points, you take the differences, and you get your slidable vectors. And these are the things, these slidable vector, these coordinate points, these are the things that behave like this. And so anyway, so that's the connection between arrows and a sort of a big new example from this. Let me